evaluate the limit. Here we have the sum of two terms. So we can write this as two limits. First thing we can do, usually if you have a problem which is complicated and it has many pieces, it is good practice to break your problem down into smaller pieces and try to solve that. So I'll call this L2 and I'll call this L1. And if you've been seeing the previous tutorials, you'll figure out that I usually start with L2. So that is actually what I'm going to do now. So it's the limit as x tends to 0 of this. And now the question is there a problem taking this limit? No, exactly. This is a continuous function. That is a continuous function at x is equal to 0. So there's absolutely no issue with plugging in 0 for the limit. We just write e to the 0 times 0 to the power of 3, which is just 0. So that is off the checklist. We are good. And next, what we would like to do is to look at the first limit, which is as follows. And I forgot to write the limit sign, okay. And there is a problem with plugging in, and the problem specifically is at ln of 0. And why is ln of 0? Why is this a problem? Because if ln of 0 is equal to some number, let's call it a, then this is equivalent to saying that there is a number for which I can raise e to the power of, and it will give me 0. And that is a problem. It's more or less a contradiction. There is no point for which you can plug into e to the x, or there is no number which you can raise e to that power of, such that you get 0. You can get a very small number if you put a very negative big number. I don't want to say minus infinity. But if you take this is only true if you take the limit. So this is one of the very famous cases where you have an asymptote. It's a well-discussed example. So this is the graph of e to the x. And e to the x always gets very close to 0, which is the x-axis, but it never touches it. There's always space in the middle. So that is the key insight. If you don't already know this, let me just briefly tell you that the ln function and e to the power of something function are inverses. So I think this is the graph of ln of x for your reference. Good. Maybe I'll keep this on the side. And we can now proceed with more problems. So this is why we have a problem with saying that with saying that ln of 0 is equal to something. So that is a problem. And the solution here is this term. Maybe this term will change something about this setup that we have. And indeed, this will turn out to be true. Now, notice that I can just simply write square root of x as x to the power of half, 1/2, and then I'm multiplying by ln of x. And because I'm doing that, then this is a polynomial, and ln of x grows slower than any polynomial. So that is also another key piece of info. And this is one we use here. And if it grows slower than any polynomial, then x to the half will go to 0 before ln of x goes to minus infinity. Because it's going to minus infinity, it's going very slowly. And that is the trick. So in that case, we get that this limit is equal to 0. And this should be your answer. So the answer to the limit should be equal to 0. Now, if you would like to see more details on this fact, why this is true, stick around. I'll give an argument now. But if not, you can feel free to end the video here. So why does this actually work? Why does x to the half grow faster than... what does this have to do with going to 0 or going to infinity or all of that? These are good questions we can ask. And usually the way to argue for such things is by using u subs. And so this is what I'll do now. I'll say maybe u is equal to x to the half. So notice that if x is going to 0, then x to the half is also going to 0. So I'll replace x goes to 0 with u going to 0. I'll put u here instead of x to the half. And I'll put, instead of x, I'll put u squared. Because if u is equal to x to the half, I just square both sides. And then they cancel out, I get x to the 1. It's very nice. I will not write this down. And then I can use the property of the logarithm. So this is actually equal to 2 times u times ln of u. And then, okay, by the same argument, this is a polynomial which goes to 0 faster than the logarithm function, because the logarithm grows slower than any polynomial. So this should be 0. But if you even want to go further, let's say you're just having fun at the moment and you really want to take this one further step, you can choose w to be equal to 1 over u. Then if u is going to 0, then w, which is 1 over u, is going to plus or minus infinity, right? So it's either plus or minus infinity. And then we will substitute once again. So I'll put w instead of u, and I'll write plus or minus infinity. If u is equal to, if w is equal to 1 over u, then u is equal to 1 over w. Instead of u here, I'll write 1 over w times ln of 1 over w squared. Well, 1 over w squared is equal to w to the minus 2, just in an exponent form. And then I use the property of the logarithm once again. So all of this is happening inside of the bracket. Yeah, let's not forget to include the factor of 2 here. Oh, no, it doesn't have to be included. I'm sorry. Yeah. So what we do now, we take the power which is minus 2 outside. That's now minus 2 outside. And then I have ln of w, because the power is now gone, and I'm dividing by w. And now I can also use the same fact, but now it is more obvious that if I take the limit as w goes to minus or plus infinity, now it is more clear, I think. When I say it goes to 0 faster, maybe that doesn't make much sense. But here, if I say going to plus or minus infinity, and we know that ln of x grows slower than any polynomial, and this is clearly a polynomial, I mean it's a degree 1 monomial, but it is still grows faster than ln of w. And if that is the case, then the denominator blows up into a very big value. And if you are dividing the small number by a very big value, then you get 0. So you should get minus 2 times 0, which is 0. And another analogy for this that I just thought of, you can buy a pizza and you can divide it on 1 million people, for example. There's not going to be enough pizza for everyone, right? Same concept, more or less. But in essence, this is the key fact that you need to know for this exercise.